Here's the last section of Chapter 6 where we're going to learn how to find the standard deviation of binomial random variables and what they mean, as well as a new type of random variable, geometric random variables. We're also going to learn a little bit about how binomial random variables, after lots and lots and lots of trials, start looking normal. And how we can use that and when we can use that, but that's not required for the test. So we're just going to brush through. So we have here a binomial distribution of something we've looked at previously, which is the probability that a family with 5 children where the probability of getting type O blood is 25%. So this is binary. This is binomial because A, there's a probability of success of getting it and not getting it. Then you're looking at each individual trial is independent, and then we're looking at the number of trials is 5, and then we know the probability. So quick reminder, we would, for example, to find the probability that one kid gets the O-type blood, we would go ahead and take 5 take 1, which would be 5 factorial over 1 factorial over 4 factorial, which works out to be 5. And then one of the kids getting it and 4 of the kids not getting it, that works out to be 0.3955, or about, there's a 39% chance, 39.5% chance that you're going to have one kid with type O blood. So this is the distribution. If we were going to talk about the distribution, we're going to talk about it the exact same way we talk about any other kind of distribution. We look at the shape. In this case, the shape is slightly skewed to the right because you have a better chance of 0, 1, or 2 of the kids getting the O-type blood than 4 or 5. And the median and the blood type is 1. You can see that pretty quickly. And then if we were to use our formula for the mean, and I'm going to So we can do the mean the long way, like we've learned how, which is to add up 0 times 0.2373 and 1 times 0.3955 and 2 to add them all up, and you get the mean is 1.25. Interpreting that, we know that the average number of kids that if there were lots and lots of families like this, the average number of kids that would get this O-type blood is 1.25. And then if we want to look at the variance, we could start by looking at the variance itself, which is adding up the individual value minus the mean, so 0 minus 1.25, square that times the probability at that one. We could do it the long way, and our variance would be 0.9375, and then we would take the square root of that to find the standard deviation, and then we could say that the average deviation from the mean is at 0.968. or approximately 1 kid. This is the long way. We can do this the long way no matter what. And only if it's binomial, it's super easy. You can go ahead and find the mean of x, or the expected value of x, by taking the number of trials and multiply it by the probability. And if you want to find the standard deviation, you find the variance by taking the trials times the probability times 1 minus the probability, or its complement. Then you take the square root to find, because this gives you the variance, and then you take the square root to find the absolute value. Goodness, to find the standard deviation. And we're doing an example. So here, if we have this situation, there's this tap water experiment that sometimes gets done in class, and Ms. Shear said it wasn't worth our time. But in it, you were given 3 different cups, 1 that has tap water and 2 that has bottled water, and you're supposed to see if you can tell the difference. And so if they have figured out through doing this lots and lots of times, and of course our class would be different, that 21 students were looked at, and they had a third of a chance of guessing correctly. We're going to stop right now, check to make sure this is a binomial situation, correct or not correct, binary, independent. Each kid's guessing is not dependent on anybody else's guessing, fixed number of trials, 21 students, and then we know the probability ahead of time. It's the same, it's 1/3. So we can go ahead and use that formula that we saw on the previous slide. The average is going to be n, which is 21, times 1/3. So the average number of students who guessed correctly is 7 students. Make sure you can interpret what these averages mean. And then also, so we expect about 7 students to get it right. And then the standard deviation would be that 21 times the 1/3 times the complement, or 1 minus p. So when we calculate this out, we get 14/9. That is the variance. So then we're going to go ahead and take the square root of the variance, which is the square root of 14/9, which would go ahead and give us, I believe, 2.16. Not 2.16, 2.49, 2.419, so 2.419. So that means typically the number of students who got it right varies from by 2.419. So one of the things that we need to talk about is binomial distributions that work out to, that are used very, very commonly in statistical sampling, where, like the example on page 401, where it looks at 10,000 flash drives, and they're choosing to pick 10 randomly to see if there are any flawed drives, and 2% of the drives in general are flawed. So we could look at the probability, the correct probability, because when we take 1 out, it's going to be 9999 out of 10,000, etc. Or we could use binomial distribution and use the formula. And the agreement within the statistical community is if your trial is less than 1/10 the population, then you're fine. So if you're picking 10 out of the 10,000, then that fact that you're not replacing is not going to be a big deal. But if you took 1,000 out of 10,000, you're right at that edge where you're possibly going to screw up the statistics, because you're taking so much of that population away. This is not going to be something that's we're going to be testing this time, but I wanted you to understand that there's parameters that are used. Same thing also, we begin to see, and this is something that we're not going to test on right now either, but if binomial distributions, when the trials gets more and more, gets closer and closer to a normal approximation. So if you have enough data that the following checks are in place, that if I can take I'm going to use this big one that looks very much normal. If the trials times the probability is greater than or equal to 10, and then the trials times its complement is greater than or equal to 10, greater than or equal to 10, then we can go ahead and use all of the properties of the normal curve. So let's check. So if we look at this one above here, when n equals 50, and we multiply times the probability, we get 40, and we multiply by its complement, we get 10. So once we get to that point, we can go ahead and use all the properties of the normal curve. We can find the probability that it's going to be above 40, all of those things. So geometric settings have some things in common with binomial settings. They're binary, so you either have a success or a failure. Each of the things are independent, and you know ahead of time the probability of a success. This is the part that's different. In a binary setting, the n is fixed, and in a geometric setting, we're looking for how the number of trials it takes to get one success. So we're actually going to use traditional multiplication rule of independent events for finding a geometric setting. So here we have just an explanation really quickly about it. You can read this as well as I, but I'll just go ahead and read it to you. In a geometric setting, if we define the random variable y to be the number of trials needed to get a success, then it's geometric. And the probability distribution is called a geometric distribution. The probability of the possible values of y are 1, 2, and 3. It takes 1 time or 2 times or 3 times. Remember that for binary, It could have been from 0 all the way to n, and geometric it's 1, 2, and 3. It's important to be able to distinguish it. So if you see the B and the I and the S, then you look for the distinguishing factor. N, if you know it ahead of time, then it is binary. And if you are looking for how many, then it's geometric. So this is a game that's in the textbook, where basically you randomly pick a day of the week, and then a random number generator picks a day of the week, and if you match, then you get less homework or something like that. And so obviously the probability of getting, here it's geometric, so we're waiting for how many times it's going to take before the person guesses correctly. So the probability, so it's geometric because you're waiting for that time that it gets, but you have the probability, and that's the only parameter that we need when we have geometric, is the probability of a success. So the probability that y is 1 is 1/7. So, because that means that on the first person's guess, they got it right. So if the probability that y is 2, the first one's going to be the failure rate, and the second one is going to be the success rate. And they multiply the two together to get the probability. The third one is going to be 2 failures, and the third one's going to be a success. And so in general, whatever k is, you're going to have 1 fewer than k with the complement, and then the probability of a success being your last one, because these are all of these failures as many times as k is -1, and then a success. For this would be if y was equal to 4. There'd be 3 failure rates and 1 success. So with geometric random variables, here's our distribution that's been calculated using the formula, and you can go ahead and notice that in general, in this particular case and in general, the shape of a geometric random variable is going to be skewed to the right. The highest probability is it's going to take 1, and then it's going to be a slightly lower probability for 2, et cetera, et cetera, et cetera, and getting smaller and smaller and smaller as you head away from one trial. In this case, the number of guesses. It's always going to be skewed. The center has a formula, and the formula is you're going to go ahead and take the probability and take its reciprocal, 1 over the probability. So in this particular case, the probability is 1/7. So the expected value, or the mean, is going to be 7. We don't use the standard deviation as much for geometric, but it's very similar to the formula for binomial. You're going to go ahead and take that mean, and you're going to take the mean -1, and so to find the variance, and then take the square root. So it's basically the mean and the mean -1, but in this case, geometric would be 1 over the probability, and binomial would be the probability, and the probability -1. But we don't find the standard deviation of geometric as much. You'd just be asked to here we go. That's what you need to know.